In this video, we're going to be looking at using our area model to help us find the real roots of polynomials. I have a first problem up here asking us to find the real roots of x cubed plus 3x squared minus 4 equals 0. I've already generated a graph of y equals x cubed plus 3x squared minus 4 to help us identify the possibilities. We already have seen in previous videos that in identifying what the possible roots of this are, we focus on what the c value is and on what the a value is, the leading coefficient and the constant. And our factors of the constant are plus or minus 1, plus or minus 2, plus or minus 4. And the factors of the leading coefficient, since it's just a 1 here, are not going to alter those at all. When we see in the graph, it looks like we've got something happening at -2, something happening at 1. So those involve these here and not that one so much. So we just pick one that we're going to do our long division with. We'll go ahead and go with the root at 1, which means we're going to be dividing by x minus 1. And so we get our area model set up, and the first thing that we need to create is the x cubed right there, and then just following the pattern that we've done before. That means this has to be an x squared right there. That gives me a minus x squared down there. We draw in the next box. We know that these two on the diagonal here have to add up to 3x squared, and that's a minus x squared there, so that must be a 4x squared right there, which means that this would have to be a positive 4x. And of course, if that's a positive 4x and this is -1 here, then we get a negative 4x. And in our next boxes here for the linear, there is no linear term in this, so those have to add up to 0x, which means this would have to be a positive 4x, which would make this a positive 4, and that would make this a minus 4, which, of course, if we continue the pattern here, we want these two boxes to add up to -4. The -4 is already there. This becomes our remainder of 0. So this thing factors into our x minus 1 that we divided by, and an x squared plus 4x plus 4. And we continue to try to factor this thing. We want to try to break it into linear pieces if we can. And so here we've got the x squared plus 4x minus 4, and we're going to try to break that one down. Everything seems to indicate that an x plus 2 is going to make that happen by what we see in the graph. And so this x squared goes right there, which means that would be an x, and that would be a 2x. And we want the things on the diagonal here to add up to a 4x, which means this would also have to be a 2x. And that makes this up here a 2, and makes that a 4. And again, our constant terms are supposed to add up to a 4, so we get the remainder of 0 that we were looking for up here, and that tells us that this second part factored into an x plus 2 and another x plus 2, and we have an x minus 1. That was all equal to 0, so using our zero product property, we can say that either x minus 1 has to equal 0 or x plus 2 has to equal 0. So x equals 1 and x equals -2 are the real roots of this polynomial. Now, we can see that the x minus 2 shows up as two different parts here, and we have a name for that. Okay, The idea is that when that happens, we call that multiplicity. So here is a definition for us that says the multiplicity of a root r is the number of times that x minus r is a factor of p of x. So in this case, our x equals 1. The x minus 1 was a factor 1 time, so this has a multiplicity of 1. But the x minus 2, this one showed up as 2 pieces, or the x equals negative 2, came from 2 different x plus 2's, so this one has a multiplicity of 2. And though we're not completely ready to talk about it right now, we get some idea of what that multiplicity of 2 does versus a multiplicity of 1 when we compare where these roots are on the graph. And so there's our first example of finding the real roots of polynomials. Let's take a look at a second one. So in example 2 here, we're going to find the real roots of x cubed plus 7x equals 6x squared. Well, the first thing we need to do is make it say equals 0. So we'll subtract a 6x squared from both sides, 0. And this has a feature that I haven't done in a video yet, but we should recognize that sometimes we can make the problem much easier by just looking and seeing that we have greatest common factors. So in this case, I do have a greatest common factor. Every term that's in here has an x in it, so I'm going to start by factoring that out. If I take that out, I get an x, and that would be x squared minus 6x plus 7 equals 0 is what is left over. And so now I can go straight to just factoring a quadratic here. Although we'll find, I'll demonstrate here, that if we check this with the discriminant, the part that's under the square root in the quadratic formula, we get a b squared, which would be 36 minus 4 times 1 times 7. So that's a 36 minus 28, which is 8. And 8 does not have a nice square root, so this is not going to be rational answers. It's going to be irrational answers. They are going to be real because this is positive, but that also means that we would not be able to factor this. So in hunting for our other roots, we need to, well, I guess we first of all recognize that this means that one way to make this 0 is for x to equal 0. So that is one of the roots that we're looking for. We'll find the other ones by doing the quadratic formula. So we get x equals the opposite of negative 6, which is a positive 6, plus or minus the square root of 8. We already figured out what was going to go under that square root over here, all over 2 times 1. And so a little bit of simplifying here, and we're going to get 6 plus or minus 2 root 2 over 2, which we could factor a 2 out of the numerator there and get 2 times 3 plus or minus root 2 all over 2. And this 2 divided by 2 is just 1. So we get that x could equal 3 plus the square root of 2, or x could equal 3 minus the square root of 2. So those are 2 different answers. We only have multiplicity 1 on everything that we're doing here, but we do have 3 different answers to our cubic. And you'll notice the pattern on these irrationals that we have here, that they have that conjugate kind of feel that we looked at with the imaginary and complex numbers, though these are not imaginary and complex. But we do have this, the irrational root theorem. The irrational root theorem says that if a polynomial p of x, like our x cubed minus 6x squared plus 7x here, has rational coefficients, which it did, of 1, negative 6, and 7, and a plus b root c, is a root of p of x. So this is an example of a plus b root c. There's a root of p of x equals 0. Then a minus b root c is also going to be a root of p of x equals 0. So these always come in these pairs like this when they are irrational. Otherwise, we won't end up with rational coefficients. All right, and that's my examples of how we find the real roots of polynomials.